Chapter 1, Section 4 is on continuity and one-sided limits. Now, continuity we've talked a little bit about before, but we're going to define it. And when we talk about a well-behaved function, as I mentioned in the last video, a well-behaved function is a function that's continuous. There aren't any breaks. There aren't any sharp corners. Sometimes they're called cusps. There are no holes. There are no gaps. There are no vertical asymptotes. We say that a function is continuous, just like the word continuous means without stopping in a normal conversation. So in this case, we're going to look at the three things that can happen that shows a lack of continuity, and then we're going to kind of see if we can define continuity first at a point, and then at an interval, an open interval, and then at a closed interval. And of course, the closed interval, when you're looking at the endpoints, that's where we come in with the idea of what we call one-sided limits. So first off, notice here that on my function, let's call it y equals f of x, at c there is a hole in my graph. So f of c is not defined. Now the limit might still exist, but the function f is said to be not continuous at x equals c. Here's another situation. This one doesn't have a hole in the graph, but there's a break or a gap in the graph. Here at x equals c, it's actually defined. Whatever this value is up here, it's actually defined. The function is defined at c, but we say that the limit does not exist because the limit from the kind of like values less than that, or from the left side, are not the same as the values from that are greater than c, that are kind of on the right side of c on the number line. So we say the limit as x approaches c of fx doesn't exist. D and e does not exist. And then we have one where the limit exists, and where the function is defined, but it's not defined at that value of limit for that particular function. It's not defined at x equals c. I mean, it's defined here, but it's not filling in the hole. There's still that gap there, that hole in the graph, that shows a lack of continuity. So we say that a function is continuous at a point if all these three things do not happen. A function is continuous at c if the following three conditions are met: that it's defined, that the limit exists, defined, that the limit exists, and that the limit as x approaches c of our function f of x is equal to f of c, where we could use like a direct substitution. Now, that's continuity at a point. You say, well, I mean, if you have a function and it's over the set of real numbers, there's no way you could figure out continuity at every single point. Well, we're going to make some generalizations, but we start off typically because continuity or a lack of continuity typically happens at a particular x value, at a point. So a continuity on an open interval just means that it's continuous if it's on the open interval, if it's continuous at each point. And again, you can't actually go through and plug in and go through these three steps to show that it's continuous at every point on an interval, because there's infinitely many points. But we say that a function is continuous on an open interval a, b if it's continuous at each point. And if it's continuous, a function is continuous for all real numbers, then we say it's continuous everywhere, or even cooler, we say it's everywhere continuous. All right, so that's kind of cool. Let me move this up just a little bit. All right, now, if f is not continuous at c, then f has discontinuity at c. And there are two types of discontinuity, what we call removable discontinuity and non-removable discontinuity. Now look at the examples that I have above. You see how there's a hole in the graph here, but there's a gap here? You can fix this graph by defining what your function is at c. You could fill in the hole, right? But you can't do that here because you can't fill in a gap. There's infinitely many points in between. So this type of discontinuity would be called removable, but this kind of discontinuity would be non-removable. Now over the third case, this would be removable because all you'd have to do is redefine this point to be right there at that value, and that would fill the hole in the graph. So they're removable and non-removable. Now it says discuss the continuity of each one of these functions. Well, at each one of these functions here, we have a rational function here at a. Notice that x cannot be 2. We would have graphically a vertical asymptote at x equals 2. So if it said discuss the continuity, we would say it's continuous or from negative infinity to 2 and from 2 to infinity. Well, stereo is acting up. Let me go turn that off. Wasn't very loud anyway. Didn't want you guys to be bothered by it. All right, so now we'd say that, discuss the continuity, we would say it's continuous for all values of x except at 2. Now you say, what happens at 2? Well, it's discontinuous at x equals 2. And what type? Because of the vertical asymptote, it is non-removable. Okay, if it has a hole in the graph, then it's removable. Now, speaking of hole in the graph, look over here. This is equal to x minus 2 times x plus 2 all over x minus 2. We do not have a vertical asymptote at x equals 2. We have a hole in the graph because 2 makes both the numerator and the denominator equal to 0. So we still have discontinuity at 2. We just have removable discontinuity at 2. So this thing is continuous, just like the other, from negative infinity to 2 and from 2 to infinity. Okay? Now, the point of discontinuity, x equals 2, in this case is removable because it's a hole in the graph as compared to having a vertical asymptote there and it being unbounded. All right, here's another function. This is a multi-ruled function, and it says h of x is equal to x plus 2 for all values of x less than or equal to 0, and it's equal to x squared plus 2 for all values of x greater than 0. Well, if you looked at this graphically, because it's kind of hard to picture sometimes doing one of these things, trying to picture what's going on in your head when you have more than one rule here. This graph would be a line with slope 1 and y-intercept at 0, 2. So this is for all values of x less than or equal to 2. It would look something like this. This is really rough. Hopefully you can see that okay. But then for x greater than 0, now see, if you substitute 0 when you'd be back at 2, it'd be an open circle here, but it's already filled in from the other half because of the equal to. And then this is a parabola, so it kind of goes up like this. And so as you can see here, there is no hole, there is no gap. This is filled in, so this is continuous everywhere, or everywhere continuous. Continuous, I'll just abbreviate, from negative infinity to infinity. Now the same thing's going on here with the cosine of x, because you guys know what the graph of the cosine of x looks like. It's a periodic function. This is going to be really rough. It's going to look something like this. And this is going to continue forever and ever and ever, as you know. So this is continuous everywhere, or everywhere continuous as well. So I'm going to write that it's continuous from negative infinity to infinity. So there are some examples where we have continuity on either some kind of a restricted domain because of a variable in the denominator, or in this case was defined for all real values. Now, to consider continuity on a closed interval, then we have to think of the idea of what we call one-sided limits, which we've kind of talked about but never officially stated. Okay, a one-sided limit means that we're only looking as x approaches c from either the values that are bigger from the right or the values that are smaller from the left. Okay, so in this case, when we look at a right-sided limit, let's go back to, let's say for example, this function here. If we looked at values that were approaching it from the left side, then we would use this rule here. As x approaches 0, the limit would be 2. If we look at it from the right side, for values greater than 0, then we would be looking at it using this rule right down here. All right, so now f is continuous on a closed interval, including the endpoints a, b, if f is continuous at every point in the open interval, and if we have this to be true, that the limit as x approaches a from the right side, this is for the left endpoint, from the right side for values that define in this interval, of f of x is equal to f of a, and also on the other endpoint, the right endpoint, we look at the limit as x approaches b. Notice the little negative sign means from the left side of f of x is equal to f of b. So if I said evaluate the one-sided limit here, the limit as x approaches 2 from the left side. Now from the left side would be numbers a little bit smaller than 2. Like 1.9, 1.99, 1.999999. Well, if I plug those numbers into here, 1.9, 1.99, 1.99999, and I square those, this is getting closer and closer to 4. So I have the square root of 4 minus values that are getting closer and closer to 4. And so we would say that the limit here is equal to 0. Now, I didn't ask, but if I said, what's the limit as x approaches 2 from the right side of this square root of 4 minus x squared. Well, in this case, this is not going to exist because now I'm going to be taking numbers a little bit bigger than 2. 2.1, 2.01, 2.0001. And if I plug those in, then this is a little bit bigger than 4. 4 minus a little bit bigger than 4 is negative, and I'm taking the square root of a negative. So in this case, this one does not exist. All right, over here, I'm taking the limit as x approaches 1 from the right side, so a little bit bigger than 1. 1.1, 1.01, 1.0001. And I plug those in, and this is getting closer and closer to 1, but it's still a little bit bigger than 1. Minus 1 is going to be getting closer and closer to 0, but because it's a little bit bigger, it's still positive, and you can take the square root of a positive number. We can say that the limit here does indeed equal 0. Now this guy here, you should remember from your Algebra 2 and your pre-calculus days, this is the greatest integer function. And they kind of use like double brackets on each side. And the greatest integer function talks about what happens as you, if you plug numbers in, it's the greatest integer less than or equal to the value. Now you may remember that the graph looks like what we call a step function. Now this is going to be really rough because I did not think to draw out a set of axes ahead of time. So I'm doing it now. This is, by the way, kind of a long section in the book. And I used to usually take 2 days in a traditional classroom setting to go over all the material, which is kind of ironic because the lesson is on continuity and I would have to break it apart. But anyway, the greatest integer function kind of looks like this guy here. The greatest integer of 0 is the largest integer less than or equal to 0, and 1, and so on. And you can see why it's called a step function, because it kind of looks like stairs or steps. And this continues this way and this way forever and ever and ever. Here's 2. We're looking at the limit as x approaches 2 of the greatest integer of x. Well, if we approach 2 from the left side, notice that the values are 1. So if I write the limit as x approaches 2 from the left side of the greatest integer of x, it would go to 1. But if I take the limit as x approaches 2 from the right side, we were just talking about one-sided limits, as x approaches 2 from the right side, that would be a little bit bigger than 2, 2.1, 2.01 and such, and it's equal to 2. So that doesn't make sense. It doesn't make sense that we have 2 limits, 2 different values here. So what we're going to do here is we're going to state that the existence of a limit, that a function f be a function, and let c and l be real numbers, the limit of f of x as x approaches c is equal to l if and only if, if and only if, the limit from the left side equals l and the limit from the right side equals l. So in this case, because the limit from the left doesn't equal the limit from the right, this does not exist. Now, if you had a problem like that and you had to kind of show, not just put down an answer, does not exist, you would show how the limit from the left differed from the limit from the right. And this is the theorem that says that. Okay, very important theorem. Okay, now we've looked at continuity on at a point. We looked at continuity on an open interval. Now we have to look at continuity on the closed interval, now that we have officially talked about right-handed and left-handed limits. A function f is continuous on the closed interval AB if it is continuous on the open interval AB. Seems like I said this before. Did I write this theorem down twice? Heavens to Murgatroyd if I have. Well, I kind of informally stated, but here's the formal definition here. If the on the open interval AB, if the limit as x approaches a from the right of f of x is equal to f of a, and the limit as x approaches b from the left side of f of x is equal to f of b, so we include the endpoints. A function is continuous from the right at a, that's this part, and continuous from the left at b, that's this point here. So it has to be continuous at all the interior points, and then it has to have continuity from the right and continuity from the left at the left and right endpoints respectively. So now if I say discuss the continuity of f of x equals the square root of 9 minus x squared, I would have to consider the limit as x approaches as in this case, this is defined from -3 to 3. Remember that 9 minus x squared has to be greater than or equal to 0. So 3 minus x, 3 plus x has to be greater than or equal to 0. I get key values here. Let's write key values here of x equal 3 and -3. So on the number line, if I take a value from here in this interval like 10, I would get negative times positive is negative. Here I would take a number like 0. I get positive times positive is positive. -10, positive times negative is negative. I want it where it's greater than or equal to 0. I want right here between -3 and 3 inclusive. So this is going to be something to discuss here, whether or not this is continuous on its entire domain. So I'm going to have to consider the limit as x goes to -3 from the right side, as it approaches -3, of the square root here of 9 minus x squared. Well, as x approaches -3 from the right side, that'd be like -2.9, -2.99, -2.99999. When you square those, it becomes positive and a little bit smaller than 9. So the limit is going to go to 0. It exists. And also, the limit as x approaches 3 from the left side approaching 3, a little bit smaller than 3 of the square root of 9 minus x squared, 2.9, 2.99, 2.99999. Well, those values come in here, get squared, and are a little bit smaller than 9. So 9 minus 9, I get the square root of values going to 0. It's equal to 0. So I have continuity on the right. I have continuity on the left. And because this is defined in here, and we have a nice function without any breaks, we have a nice composite function, this is continuous on the closed interval from -3 to 3, everywhere it's defined. All right, now there's some properties of continuity that come in handy. I've got them listed here. If b is a real number and f and g are continuous at x equals c, then the following functions are also continuous at x equals c. This is really nice for a lot of the functions that we're going to be talking about, polynomials and such. We have a scalar multiple, that if your function f is continuous, that a constant times that, or a scalar times that, means the function is still continuous. The sum or difference of two continuous functions is continuous. The product of two continuous functions is continuous. And the quotient of two continuous functions is also continuous for all values where it's not going to give me 0 in the denominator. So as I mentioned before, this type of theorem tells us that we've got all sorts of continuous functions: polynomials, rationals, radicals, and trig functions. Now if you have a composite function, it's like we were talking a little bit before about evaluating limits of composite functions. We can use that definition to help us with this theorem. If g is a continuous function at c and f is continuous at g of c, then the composite function given by f circle g of x, which of course is f of g of x, is continuous at x equals c. So that's saying that the limit as x approaches c of f of g of x is equal to f of g of c. And that again comes from the last section. All right. Now, let's talk a little bit more about continuity. Let's discuss the continuity of the following functions. I've got 3 of them here. Now, notice that the first function, f of x, is equal to the cotangent of x. Well, you may remember, although it's probably been a while since you graphed the cotangent function, so let me grab my graphing calculator here, and let us get ready to do some graphing here. So we're going to do, what do I have, the cotangent, so that would be 1 divided by the tangent I can just get this in here, the tangent of x. And let me make sure that my zoom here is set up right, and you can see what the graph looks like, and you can see the asymptotes that are being drawn in as well. We have a function that is not continuous at certain values. Now, what values is it not continuous at? Well, at where the x values are for your vertical asymptotes. So remember that cotangent is the cosine of x over the sine of x So we'd have to look to see where the sine of x is equal to 0. Well, the sine of x is equal to 0 at 0 and at pi and at 2 pi and so on. So and all of its opposites. So x, let's go with 0 plus or minus pi plus or minus 2 pi and so on. We would say that it's continuous. Now this is going to get a little tricky looking. It is continuous from pi k to, let's see if I can write this so that it makes sense, pi k plus 1 in parentheses from the interval from pi k, where k is an element of the integers. So like if, for example, k is 0, then that would go from 0 to pi. If k is 1, that would go from pi to 2 pi. So it's excluding all these values here. And this is how we could write that it's continuous. And I'm just going to abbreviate continuous here. Now, what a lot of people will do when it says discuss the continuity is they'll say it's discontinuous at x equal pi k, where k is an element of the integers. And then they kind of figure, well, that kind of covers it. Well, it doesn't really say discuss the discontinuity as much as it says discuss the continuity. So that would be a little tricky to write out. Okay. The next guy up, g of x is equal to the sine of 1 over x, and also at 0 here, and it's asking for where do we have as far as continuity. Well, I don't know if you remember this guy from before, but I'll go back and I'll see if I can put him on let's see if, hang on a second here, let me second quit, let me go to y equals, let me clear that out, and let me type in the sine of 1 over x, and I'm almost there, sorry about the delay here, and let's go ahead and look at the graph here. Now I know you can't really tell because I had when I did this in the previous video, a couple videos ago, I had this as a much tighter picture on the x. This thing just goes crazy, bouncing back and forth in between. It says that it's at 0 when x is 0, but it's not going to ever zoom in on a particular value here. So it doesn't matter that it's actually defined here. This is not going to give us the kind of value that we're looking for, and this is not going to be continuous at 0. So it is continuous from negative infinity to 0, and then from 0 to infinity. And we have non-removable discontinuity at x equals 0. All right, now this guy, because you put that x in there, as x gets closer and closer and closer to 0, this value gets tighter and tighter. Now, granted, this is bouncing back and forth, but this is approaching 0 right here. If I was to look at the limit here, as x approached 0 from either the right or the left of x times the sine of 1 over x, this part here is going to be going to 0 here. This part here is bounded between 1 and negative 1. And so this is going to 0 times something between 1 and negative 1. This is going to approach 0. So this is going to be continuous everywhere. It is defined at 0, and we can write that it's continuous everywhere, or everywhere continuous, from negative infinity to infinity. All right, now, this next theorem is called the intermediate value theorem. You can already see it coming, and it has to do with how functions behave on a closed interval, functions that are continuous on a closed interval. And this is something you're certainly going to be seeing on the AP test. As I mentioned, this is a long section, guys, but we are getting closer and closer to being done with this, as we have just a couple of ideas left here. Let's see. I feel like I'm missing a sheet of paper here, that there's one more page to this. Perhaps not. Perhaps this is what we finish with. All right. So now, the intermediate value theorem says that if f is continuous on a closed interval from a to b, and k is any number in between f of a and f of b, then there's at least one number c in the interval, in the closed interval from a to b, such that f of c is equal to k. Now, it doesn't tell us how to find c. It just tells us that c exists, which means that it's an existence theorem. Okay? An existence theorem tells us, hey, it's there, I just don't know how to tell you how to find it. And this proof is based on what we call the property of completeness. That's the idea that you have a function that's continuous. There's no holes or gaps on the real number line. And this is really kind of a convenient way before technology improves so much to help us to be able to estimate zeros on a function. Now think about what it's saying. I'm just going to roll this back just a little bit because I'm going to need some space here. If I have a function here and it's continuous from A to B. Okay? Now what this is saying is in between A and B there's going to be some value, they call it C, such that if you plug C in you will get every value in between f of A and f of B. For example, if I wanted to find this value right here, whatever this might be, that value exists. There's no holes or gaps in there. And what's really nice is, look, it crosses the x-axis. So I know that I have a 0. If this is negative and this is positive, I know I'm going to have a 0 in between because 0 is one of the numbers in between a negative number and a positive number. So that's why I said it's very useful for finding the zeros of a function. So let's say it says for the function f of x equals x to the third minus 2x minus 3, determine if there's a 0 in the interval from negative or from positive 1 to 2. All right, first things first, f is continuous, okay, on negative or on 1, 2, since it is a polynomial function. Okay, that's a qualifier to use the intermediate value theorem. It has to be continuous. It has to be continuous. So I make that statement that says that it is, and I explain why, because it's a polynomial function. We just determine that those are everywhere continuous. So now I look at f of 1. F of 1 is 1 to the third minus 2 times 1 minus 3, which is going to be negative 4. I look at f of 2. F of 2 would be 2 to the third minus 2 times 2 minus 3, which is positive 1. So see, I have f of 1 is negative, f of 2 is positive. Because of the intermediate value theorem and because 0 is in between those two numbers, there guarantees me at least one number c such that f of c is going to be 0. Okay, therefore, by the intermediate value theorem, we are guaranteed at least one c such that f of c is equal to 0. Okay, this value c being between 1 and 2, which means f of c, which of course is 0, is in between f of 1 and f of 2. Negative 1, negative 4 and positive 1. Alright, so we're guaranteed that 0. Now, what is the actual 0? Well, the actual 0 is a little tougher to figure out, but we could use what we call the bisection method. Now, I don't know if you guys have ever watched The Price is Right, but there are occasions where they play a game where they have to guess the prize, and the host, whether it's Drew Carey or Bob Barker in the old days, used to say higher or lower based on their guess. If they said $400 and he said higher, so they might go to $500, and he would say higher, then they'd go to $600, lower. Well, then a lot of times what they would do, since they know it's between 500 and 600, they'd go halfway. If halfway, they'd say 550. Well, at 550, if he said higher, then they knew it was between 550 and 600, so they might guess 575. If he said lower, they might guess 525. So what I could do here, and I didn't give myself enough space, which makes me think I have another sheet of paper somewhere to find, is that if I look up f of 1.5, which would be 1.5 to the third power minus 2 times 1.5 minus 3, 1.5 times 1.5 is 2.25, minus 3 is negative. So see, this is negative, so that tells me that I've got now, between a positive and a negative value, that I've got my value of c pinpointed in between 1.5 and 2. So now maybe I try halfway in between 1.5 and 2. I find f of 1.75. So that'd be 1.75 cubed, which I'm going to have to probably use my calculator, minus 2 times 1.75 minus 3. Well, this is minus 6.5, so let me take 1.5 and raise it to the third power. I don't think it's going to be big enough. No, it is not. So this is 3.375 minus more than 6. So this is definitely going to be negative. So now I know it's between 2 and 1.75. And I can continue this process as many times as necessary. Now we don't really need that due to the technology that allows us just to graph this function and approximate the 0 using the trace function on your TI-84 or whatever, TI-89, whatever you're using. So anyway, the intermediate value theorem, learn it, know it, love it.